Kenneth Larsen is the product marketing director in the Silicon Realization Group at Synopsys. He's got a background in defining and executing product vision, marketing strategy, and product development. And then Marc Swinnen is the product marketing director for semiconductor products at Ansys. He formerly was at Cadence Design Systems and in marketing, product marketing, and prior to that, technical support positions at Synopsys, Azuro, and Sequence Design. So I'll turn it over to Kenneth and Marc.
All right, thank you so much. Today we are going to talk about our solutions for 3D IC designs, how it's relevant for chiplets-based designs as well. Talk a little bit about our collaboration around multiphysics analysis. So you'll hear more about that in the presentation. So in the middle of the presentation, we will kind of change hands. So, Marc, you will, of course, be presenting on the Ansys solution. So just to get the presentation started, a little bit about the motivations, what we are seeing, what's going on. We heard earlier in the presentation that there's this change, maybe going from monolithic SoCs into a system of chips. And it's changing a lot of things, we believe, in how we are going to design systems in the future. Just a little bit about the two main themes. There's one that's around disaggregation, so taking a large SoC and break it down into smaller pieces, motivated by, for example, cost and yield. And then we also have, on the flip side, integration. So we disaggregate large chips into smaller parts, and then we reintegrate them into a system, a heterogeneous system, where each of the individual parts could be, optimized within the node of that's providing the best performance, for example, or the best-in-class functionality. So these are the areas our customers have been working on for quite some time. And this spans all the various segments, high-performance computing and AI. And mobile is kind of a new area that we are learning about, where, looking into 3D stacking is becoming more urgent due to form factors and power efficiency. And then on integration of many systems or chips into one system, so for example, networking, co-packaged optics, for example, some of the new trends where we are seeing further miniaturization of systems as a new trend. And we think it's a really disruptive silicon disruption. And we need to think about new solutions for this. On the theme of today, the rise of chiplet-based solutions, a few years ago, Raja from Intel, he had this insight, and presented on 1000x more compute for AI by 2025. He talked about the history, where we started with schematics, then we went to HDL, again to design with IPs. And now many of the leading companies out there are looking into designing with the chiplets as the next level up. So chiplets kind of defined as a larger IP subsystem. Some of the benefits, so we have heard this morning, so better yields due to the smaller dies. Also opportunity to build larger systems beyond what the vertical limit is on, for example, for a monolithic die. For example, 4 and 5x vertical sizes for packages is possible. Chiplets in the optimal technology, offering some opportunities. So AMD's in some public presentations has talked about significant savings when they moved into chiplets. So there's, some additional values that's very important. Reusability is important as well. So when you're building the chiplets, you can use these chiplets in different markets and different product even. And some of the things that we are working on is, to help lower the overall system power while increasing the overall throughput of the system itself. So these are some of the areas within systems of chiplets are offering to our users and the chip maker industries. Based on the work we have been doing for many years within the multi-die designs, our engineers have put together a new platform that's enabling you to essentially work on all the various pieces that's going into a design, a multi-die design. So this includes heterogeneous system of chip design and integration of very large systems. At the recent SNOC, Synopsys user group, Intel presented that they have ambitions to put a trillion transistors within a single package in the years to come. So that's kind of really ambitious, and we hope that we can help them solve that scalability challenge. But the 3D-IC compiler is essentially a platform that's built for heterogeneous system of chip design and integration with very large systems. We have created a modular platform on top of our existing data infrastructures for our implementation tools. So we're essentially extending 2D to 3D, meaning that you can not only design world-class 2D chips, but you can essentially design many of these chips in different technologies and integrate them together and co-optimize them as one. So we have 4 areas of capabilities within our platform. The first one is around architectural planning. So in architectural planning, we are looking at the exploration and pathfinding, understanding the topology of the system that we are building, and coming up with a suitable architecture, whenever that's 2.5D, 3D, if it's sitting on a fan-out wafer level package, or any combination in between. We have design creation and integration. So partitioning out designs, managing connectivity. Connectivity in the systems that we're looking at includes hundreds of millions of connections in between all the elements in the systems. We have built, there were some questions earlier in the presentation today, we have a new checking capabilities that check 3D. So designs and all the parts, all the connection in between the chips, we check things like that. So it's kind of an extended version of LBS. Within the design implementation, I'll show some slides a little later on. We focus a lot around optimizing floor plans, ensuring correct power and clock delivery, routing of the various level of design in the entire stack, from the individual dies all the way down to the package. Integrate test, which is very important, of course. We just heard that in the presentation on chip cost. And then we are integrating our engines with our own golden sign-up tools, but also Ansys. And Marc will talk about the Electrothermal in just a few moments. So it's a new platform. We launched 3D-IC compiler a few years ago. We are qualified and certified with the main foundries. Here's some updates on that. So it's not only SoICs, but we are talking about stacking 3D chips on top of each other using direct bonding or hybrid bonding, but it's including also the entire stack for CoWos and Info as an example. Some of the highlights for our platform within system creation, we really talk about multi-die, multi-technology prototyping. So you can mix and match designs or chiplets coming from different technologies and build them together, integrate them, and optimize them as one. We do support die partitioning, all sorts of what-if analysis capabilities, and One area that's very important to support the entire stack is really to manage all the connections and the bumps in between the individual parts of the system. So we do that in system creation. In design implementation, we have dedicated routers, for example, for PCI, HBM, and upcoming here with UCIe, to automate the process and speed up the overall turnaround time for our customers and our users when they're designing these complex systems. As I mentioned, we have representation for LVS, but we also have a built-in multi-die DRC route checking. So right now in the industry, we don't have a standard for designing multi-die systems. And we have created a framework with checking that's allowing all the things on the silicon and packaging side that's required for successful tape-outs. And then I mentioned around multi-die test access. I'll show a little bit of a picture on that. So when you have known good dies, you need to be able to stitch them together. And we have solutions for that as well. Within the systems analysis, we talk about the entire spectrum of analysis, including electrical, thermal, signal, and power, both for sign-off, but also, and maybe more importantly, bringing those analysis capabilities up front in the design process. So when you're exploring architectural alternatives, that you have the power of the Ansys engines up early in the process. Our platform is, as I mentioned before, an extension of our Fusion compiler platform. We have an entire data management environment that's enabling you to build these very large solutions with potentially hundreds of chiplets within a single system itself. So first, let me talk a little bit about systems exploration at the very high level. So we do have capabilities. So for example, in the past, it was not possible, at least in the IC world, to look at the entire system as one. So for example, when you're planning your connectivities around in between dies or CSVs going through the many dies that you have in your design, you need a way to visualize and maybe use this to guide your decisions in how you're designing your designs. So we do have representation for 2.5D and silicon interposes, 3D stacks, and also the package itself. So we can represent the entire technology stack within the platform. We have created some new capabilities so we can move things around. So for example, CSV, I mentioned that, it could be bumps as well. So you can improve the overall performance of the system. Maybe you reduce the need for extra layers of RDL in the bottom by being clever with how your connectivity was set up from when you co-designed your design here. We have created a new bump creation tool as well. So there's discontinuity when you go from IC to packaging. We need to make sure that all connections are correct, of course, both logically but also physically. And we have created new tools that can handle that design process, and also when there's changes, for example, on the package or PCB side, that we can bring this back all the way back into to the IC world, if you want to call it that. We have capabilities for bump mirroring. We can automatically create the 3D top-level netlist that you would use to perform LVS style checking. All these things are kind of integrated in our platform. Abstraction is very important, and I agree with the gentleman from Cadence earlier that just having a black box is not that interesting or useful. So what we have done with abstraction is we have taken a slightly different approach. We have created the capabilities where you enable you can select levels of details that you want when you're working with 3D designs or stacking designs. And we use abstraction to be able to design systems with potentially hundreds of chiplets by removing some of the information that you don't need at some point in the design cycle. So for example, here on the left, we have an example where we're saying create a 3D abstract. It will keep all the details around I/O drivers, BOMs, bond pads, C4s, hybrid connections, or hybrid copper connections. So when you're building and evaluating your floor plans, that you have those kind of details. You can even add in, for example, your PG. So when you're planning your power deliveries, that you can take the PG and add that into your abstraction as well. So you can kind of layer the information that you have in the abstract based on the task at hand. It's very easy to go from full design view to abstract view and then go back again. So typically you will find that you have maybe engineer working on one die. Maybe he creates some changes that impact the task that you have. For example, inserting TSVs maybe, or making room for TSVs. We can consolidate these informations so you have kind of a co-environment or co-development environment for your 3D design. So you will have engineers that's working on individual dies or parts of individual dies that can come together in this environment and make sure that all the decisions get propagated to all the right places in the system. So it's easy to go forward and backward between the various abstracts. We also manage, and I mentioned this earlier, BOM management is built into the system. Here's some examples on a PCB layer where we have a lot of BOMs that's kind of getting integrated back into the entire stack of the system. And this is integrated in the tool as well. So when you're evaluating and exploring new architectures, we have a number of different methodologies. One is to look at the efficacy of the floor plans. So for example, you have two examples here where you have a bottom die, that's kind of the yellowish color. And then you have another die on top of it with regions that consumes more power. And the question becomes, how do you place, first of all, these macros, and secondly, how do you stack these things together? What's the most effective way of doing that? And what kind of analysis is available? So we have a number of examples of these designs where you can make some informed decisions on how you want to partition up your design. And we're using Ansys' excellent Electrothermal to help us give us the insight into consumptions where we have to maybe increase the density of TSVs to get sufficient power, or maybe use the TSVs as dummies to transfer away heat for certain areas of the design. So there's many options that we're enabling our customers to take. For design implementation, we have many different routing capabilities. I just mentioned a few here. So specifically, for example, HBM3, it's very narrow tolerances now. And when you're adding in many stacks in your system, having an automated solutions becomes really important. We have RDL routing, of course, bus and trunk routing, build of PG nets within the dies itself. So you can construct all these things within the 3D IC component. We also have for packaging, for example, fan-out wafer level packaging. We have an entire suite which looks a little bit different if you're a silicon designer. So the routing and the shapes and the types are different, but we do have this fully integrated solutions within the 3D IC compiler as well. So if you imagine that you go from the lowest BOMs that's touching the PCB and then all the way up, we can do all the routings of all the individual layers And maybe more importantly, we have the insight into the entire stack, so we can maybe hopefully help you optimize the design further to reduce the overall cost, optimize the connectivity, for example. I mentioned that we have some checking capabilities. Some of the examples, I think it was mentioned earlier, for example, missing bumps, bumps aligning, bad patterns. When you stick things together very closely, you need to make sure you're conforming to manufacturing rules. So we have a whole body of work around multi-die designs and all the rules and specifications that are outside what you have for the individual dies. So we create the missing pieces, I would say. That's when you're designing heterogeneous integrated solution that you really need. Quickly on integrated test. So we promote 1838. On the left-hand side, you'll see kind of a typical interposer-based design. We have some of our IPs, HBM, that's using IEEE 1500 testability connections. You can see we have 1149 as well, JTAG. And then with the new standard 1838, we get this new capability where we can test many different good dies, and we have a support for that as well. Integrated into our IPs is also analysis capabilities, so we can figure out over time if the connections are degrading, and maybe give some early indications to the users when you're kind of in field and you begin to use redundancy that you're built in for your connectivity in the design. Let me hand it over. That was quickly on 3D-IC compiler and some of the capabilities that we have. Let me hand it over to Marc for multiphysics analysis. Marc?
Yes, my name is Marc Swinnen, and I will be covering the technology that Ansys brings to the chiplet party, which is multiphysics sign-off. So Ansys has decades of experience in many different physics, including, of course, power integrity and reliability in the semiconductor space, but also PCB, thermal, 50 years of electromagnetic analysis with HFSS. We have fluidics, computational fluid dynamics, mechanical, both static and dynamic mechanical solvers. So there's a very broad range of multiphysics. And some of these seem remote from traditional chip design. But one of the points that's been brought up again and again here is that a lot of these physics are coming together. Both Sujit mentioned the multiphysics challenge, and John Park talked earlier on about worlds colliding. And that's very much the way we see it as well, is that when these design teams today are facing a problem of expertise and bringing together knowledge which is traditionally disparate. You had the packaging group, the chip group, the system group, and they all had pockets of expertise, but now these all have pulled together into a team, which, by the way, I think will pose an organizational challenge to a lot of companies as well, you know, pulling together teams that are in different countries into a unified organization. But in any case, here we'll talk about the technology. And we have a RedHawk-SC Electrothermal, which is our electrothermal analysis product for 3D-IC. That is also, we have collaborated with Synopsys to make it easily available within 3D-IC compiler. And if you look at the analyses that this performs, this is, of course, straight off IR drop and electromigration analysis, which has to be generalized across the entire 3D structure. And as mentioned by Sujit as well, there's a capacity problem here too, right? So one of the ways of dealing with this is just good cloud-based infrastructure that can handle very large sizes. The other one, and this hasn't been much mentioned, is the reduced order models that are required. If you're going to do a thermal analysis or a power integrity analysis of your entire system, you can't be dragging around everything at the transistor level. You need to have reduced order models that capture the sufficient detail and yet give you a lot of compaction. So there's that's a whole topic that we won't get into here, but the one that is worth discussing is the reduced order models. So apart from electromigration, IR drop, we also have thermal analysis. Of course, thermal is probably the limiting factor on multi-chip design here. We've seen failures in the field where designs work perfectly except they overheated. So thermal analysis is a huge one, and it's both the chip and package, and do the co-simulation of the thermal analysis across both of those. There's signal integrity on the interposer, which is a slightly different problem than, it's more a PCB type problem than on the chip. Electromagnetic coupling and interference. So one of the ways that disintegration can actually preserve performance is by having these very high speed interconnect between the chips, right? We talked about UCIe. So these chip to chip interconnects are extremely high speed. If we look at UCIe, actually, I was reading it the other day, the high speed version of the interconnect is limited to 2 millimeters. Anything beyond 2 millimeters and too much, it won't preserve signal integrity. So, and these signals have to be simulated with electromagnetics, not just the RF part, but also the high-speed digital. And then finally, there's mechanical stress and warpage. You're going to put these things together and all these tiny solder bumps, but with a differential thermal expansion, your entire multi-chip system is going to bend, warp, and expand. We have mechanical solvers built in that will also analyze that and show you where the stresses and what the material strengths are. We have material capabilities as well, so whole libraries of material strengths and expansions. So all of these are basically a multi-physics sign-off suite that provides the analysis across the multi. And so we also make a distinction between multiple physics and multi-physics, right? It's not just analyzing each one of these in isolation, but how they interact together across the system. So that's really the multi-physics challenge that we address here. Okay, next slide. Here you see an example of RedHawk-SC Electrothermal giving you a thermal analysis. And this is an interposer, a 750 square millimeter interposer with a heatsink on it. So one of the problems with thermal analysis, of course, is, well, is there a heatsink or not? Is there a fan on this heatsink? It all makes a huge difference as to what the final temperatures turn out to be. So it interfaces with our IcePack tool, which is basically a PCB thermal solver, and that can establish the boundary conditions. So based with a fan and the computational fluid dynamics to model the airflow, you can set up determine the boundary conditions, which gives you the top layer temperature of the heatsink, which allows you to analyze what the temperature inside the multi-chip package will actually be. So here you see the thermal map of the entire 4 systems. So it's a 3D package with one large SoC in the middle and 4 HBMs, high bandwidth memories, on the corners. And you can analyze this per layer. You can see the temperature distribution on the microbump layer or the substrate layer or the package top layer, the package bottom layer. And of course, you can also see these thermal distributions across the entire package, whether it be a PCB or a multi-chip package. So this is a thermal analysis package that's integrated with Electrothermal. Next slide. So here we have some examples of real cases that we've been working with customers on to give you an idea of the sort of things that we see with the thermal and multi-physics analysis. So this is a high-power HPC design, high-performance computing design. And we discovered a problem with the electrothermal issue with the microbumps. So you can see that there was these microbumps were carrying current. So Ansys technology will give you the current through each individual bump, including the Joule heating effects of that current through each bump. And so you see here on the graphs at the bottom right, the top graph, temperature graph, shows that as we go through simulate cycles of activity in this system, the system heated up and cooled down, but every cycle, it didn't cool down all the way back down. So the next cycle, it heated up a bit more and a bit more. And finally, the solder ball achieves a temperature where it goes through a phase change. In other words, it melts. And this was a catastrophic failure that was detected in simulation. But, and of course, it requires a very detailed analysis of each individual bump, the temperature of each individual bump, and the current going through each individual bump. Keep in mind that the current distribution for the power distribution for these microbumps, you have farms of microbumps. No single bump can carry enough current for the chip at top. So there's a whole series of them, and it's a bit of a challenge to figure out how much of the current is going through each individual bump. But in this case, it was able to actually determine that you were going to get an overheat situation in a particular spot. So that's one case study. Next slide, please. Here, this was working with one of our customers, Xilinx, in this case. So here we were investigating the impact of co-design, right? So on the right, you see there's we do analysis either on each individual element or as the combined system. Now, if you look at the top row, if you do a separate analysis of the package versus the chip, you actually detect that there's a pad current overcurrent condition on one of the bumps. But actually, if you put the system together, that overcurrent goes away. So trying to fix that would have been an over-design. So the combined system shows no problem there, but individual analysis does show a problem. At the bottom row, you have the reverse situation. Here you see an IR map. If you look at the IR distribution of each individual package, it looks fine, but you put them together, you're actually going to get a voltage drop situation. So co-design makes a big difference for analyzing these systems, both for over-design or under-design. And so that is one of the key elements is you can't analyze each one of these individually and then put them together and expect it all to work flawlessly and the same. So this has come, it's been pointed out several times that the analysis of the system as a whole is quite different than just slapping pieces together, even though each piece is individually at work. Okay, next one. So here's another case study. This is a CoWos design. So this is a TSMC CoWos design. And here it's once again, it's a silicon die on top of a substrate with 4 HBMs at each corner. So there's 100,000 connector bumps on this package, 10 metal layers. The board itself at 20 metal layers. So we did a thermal analysis on this system. It took about 40 hours, about half a terabyte of memory. And here you have the thermal results overview. So on the left, you can see the chip and interposer thermal analysis, or on the right, chip and interposer plus package thermal analysis, or at the bottom, chip, interposer, package, and PCB. So, this is a co-simulation across the entire system. And here you see in detail the thermal analysis on down to the individual bump level. So, which is, as we saw on the earlier cases, is a critical piece of information there. Okay, so this gives you an idea of some of the capabilities and co-simulation that we have Ansys offers and brings to the party. It's a much wider array of sign-off tools and sign-off physics than are traditionally used in chip design. But in this 3D IC world and heterogeneous integration, as John said, worlds collide. All these things have to come together. Next slide. So Ken, you want to wrap it up?
Yeah, I can do that. So what we presented is, our solution with 3D IC compiler. It's a platform to support heterogeneous design and integration. It's an open platform, so we're integrating with Ansys, for example, with the amazing Multiphysics suite of tools and products to provide value to our end users. And finally, we support co-design and analysis, which speeds up design conversions and enabling you to get optimal PPA. In the past, we talked about square millimeters, but now it's really the cubic space that we are optimizing with 3D IC. Thank you.
Thank you, Kenneth, and thank you, Mark. So one of the questions that comes up to my mind is, when you're running the simulations, you often have to set boundary conditions and meshing and decide what symmetry you need, and that usually takes an expert to do. But are there areas where the tools extensively check things? Let's say like the pin heating, will it automatically, if you put a design rule in, go do that for every pin, or does somebody have to decide to do that?
So for the pin heating, there is a maximum setup, and it will flag anything that exceeds a preset limit. So that's true. And you're right about the expertise. Somebody has to set this up. Now, this is the challenge for EDA, right? Is to the whole point of EDA is automation. We're not electronic designers, we're automators. And the whole point of these tools is to encapsulate that expertise in a way that a regular designer can use it and get useful information out of it without having to know every little detail of the meshing information. So that is the one of the reasons working with collaborating with Synopsys is to make that integration easier. Also, it's not just about setting up the problem in full detail, but a lot of the issues actually arise quite early in the design at the floor planning stage. So it's also a question of prototyping and being able to, even at the RTL stage, get an idea of, do I break it up? How do I partition my design across these multiple chips? And what are the thermal implications of that? So you want to know really right way up front before you even do physical design. If I have 2 or 3 blocks and I put them next to each other and this is the RTL roughly activity, what's the temperature going to look like more or less? And you want to avoid putting hotspots right next to each other or God forbid on top of each other. Because if you do that, you get through all your physical design and finally you do the sign off and find out this design could never have worked. It was just thermally limited. So, so you're right that there is these tools still require some expertise. They are all traditionally been built for teams that had that expertise. And now they have to be integrated and delivered in a way that encapsulates that expertise. So you don't have to be a meshing expert. You just give and import these components as a predefined rectangles and squares and whatever else shows the physical outlines, so that you can do your thermal or mechanical analysis or electromagnetic analysis without being a big expert in that. So that is a challenge, you're right.
Yeah, makes sense. Kenneth, you mentioned, and here's a question from the audience, you mentioned that disaggregation and going for 3D for mobile, people have heard it coming, but nobody's seen or heard teasers of it coming. Is there, or do either of you have anything you can comment based upon what you guys see in terms of 3D coming to mobile in the next 1, 2, or 3 years? I mean, how real is it? I mean, because I'm assuming people are doing the analysis to say, are we going to get that performance boost we think we are?
Of course, we cannot talk about specific customer cases, right? But I think we should expect it coming sooner than 3 years. There's many good reasons why this is. One is really around the functional densification, right? So it continues, and especially in the mobile segment, you don't stop adding new capabilities. Adding new capabilities typically turn into gates or transistors, which add up the space that you need to implement your design in. You have in the mobile space, you are more space constraints than you are in high performance computing, meaning the footprint that you have available and also the power and thermal envelope that you have. There's a big loss if you have multiple dies. So you try to integrate this, but splitting the dies up and have them next to each other, you probably use more energy that you really want to do. So stacking offers some new attractive ways of reducing and becoming more power efficient. You remove a set of layers of IOs, for example, that can have a significant improvement in power efficiency. We're talking significant improvements. So I think you will see it coming. And the manufacturing side is maturing as well. So it's not just, we want the designs. You need to be able to produce it in high volumes, right? But we fully expect it to come and sooner than 3 years. So.
Good to hear that. The question, and maybe this is more for Marc, but does your tool suite include magnetic simulation in the multiphysics space, for example, embedded inductors and the heterogeneous integration stacks?
Yes, very much so. We have actually the general purpose HFSS tool, which has been sort of market leading for 50 years now, electromagnetics. But we also have the Raptor X product, which came from the Helix acquisition. So Raptor X is dedicated specifically to on-silicon electromagnetics. And as Ira mentioned, it is actually much easier to use in that environment because it's designed for that, to take in those formats to produce the results in the models that the chip designers need for the simulators. So it's an optimized form of that. And yes, it does electromagnetic and magnetic, like spool coils, and can simulate those, can actually synthesize those as well if you want. If you need a coil, it can synthesize them. And actually there's a lot of savings possible in these RF type circuits. Because when you have a coil or other active elements, the fear is always, what are the interactions between them? Can I put circuitry underneath the coil or over the coil, or is that going to change my inductance? So typically people have kept them well separated from each other, which costs area. But with good analysis, you can actually fold those designs and save significant amounts of area if you can show that the underlying circuitry has no impact or insignificant impact on the inductance that you're trying to do, or the coupling. So yes, those tools are definitely available. And while it's traditionally, as I mentioned, been RF people interested in this, with today's extremely high-speed digital designs, those require electromagnetic analysis too, if you're going to get to any sort of signal integrity across those signal lines, even if they're digital.
Makes sense. Okay, let's do one more question here. On model extraction, how does model extraction differ in the 3D space from 2D, from old monolithic designs? Because they're not necessarily, and if I'm getting this question right, additive for 3D. Wouldn't 3D cause a challenge to define boundary conditions for each level versus 2D? So is there, how much, how does it differ, and how much more complex is 3D extraction?
So maybe I can start, because there's multiple, questions or answers to this stuff, right? But there's cross-coupling effects. So when you have a die, you have another die, you put them on top of each other, right? There's coupling effects, for example, when you have connections, but also if you have high-speed signals that's on both layers of the individual dies, they impact each other. So if you have a face-to-face or face-to-back configuration, there will be coupling effects. And we have been modeling these kind of multi-die scenarios for some years now. So it's not a new area, but you added many new areas that you need to consider when you're stacking things very closely, or really if you have them very closely to each other as well. We do, for example, for extraction for SIPI, we use HFSS, for example, in addition to STAR-C to handle these extractions. And both of them are enabling us to do these 3D, so we can figure out the couplings effects. Could be thermal couplings, for example. So.
Yes, to clarify, Kenneth says it's really a gamut of, depending on what sort of effect you're looking at. Some of them are simply additive, like resistance extraction, RC extraction. There you can extract each chip individually and the TSV or the bump going between them and just add them together. They are pretty much, those are simply additive. Some of them can be addressed through reduced order models. For example, the chip power model. So the power output of a chip depends on its temperature, but the temperature depends on its power output. So you got a bit of a chicken and egg there. So, but you can capture that in a chip power model and stack multiple chips on top of each other and converge on, how they influence each other, how the temperature creates the power output, which creates the temperature, and finally get a consistent solution. So reduced order models can allow you to add them together and capture the interactions between them. But some aspects are not capturable or can't break them apart into pieces. Electromagnetic interaction is one of them. The total thermal flow, right, has to be seen in the full system. So some effects have to be, captured unfortunately in full detail to get them correct. So it's really a range from additive to partially additive, or modeled reduced order models to full analysis. And sometimes you have to extract only the pieces you're really interested in. Otherwise, it becomes too complicated. And so you slice out a piece that's of interest, and the rest of it is assumed to be not that important. It's a range.
Right. Great. Thank you for that explanation. So Kenneth and Mark, I thank you very much for the presentation. So thank you.
Thank you, Aaron.
I want to once again thank our sponsors, Advantest and ASE Group. Advantest receiving the highest customer ratings in the annual VLSI Research Customer Satisfaction Survey for 2 consecutive years. And ASE Group, the chiplet era has begun, and helping drive the solutions in packaging and test to deliver these advanced packaging technology to make heterogeneous integration a reality. So I thank both the sponsors for making the event possible and free of charge to everyone. And I most importantly thank all of you for spending the time with us. Hopefully you've enjoyed the presentations, and I'd like to thank the presenters once again and wish everybody a good day. Thank you.